So reachability is the question of whether there is a path between two given vertices. So the input is a graph, and let's assume that it's a directed graph throughout this lecture, and you have two vertices, source and terminus, and you wish to know if there is a path from source to terminus in this graph. And of course one would have looked at many applications of this question, and let's not visit these applications, and we'll visit one algorithm that we will use throughout this lecture. But let's look at one question which we can answer using reachability algorithms as a black box, right? And this question is this business of strong components. So lecture will essentially be three parts, where initially for a few minutes we will talk about strong components themselves and how they have stayed in the minds of people, right, over changing times, right. So we will discuss this for a few minutes, and then we will look at reachability algorithms, look at properties of reachability algorithms, and then look at algorithms to find what are called strong components. Right. So that is the outline of the lecture here. So a strong component, right, in a directed graph is a maximal set of vertices which are connected to each other, where there is a path, right. So let us just put some of these small definitions quickly here. A strong component, right, and what you need is a digraph, and let us call this digraph D, and V stands for the vertex set, right. So which is the vertex set of D, right. A strong component C is a subset of vertices, right, and it is a maximal set. Its inclusion maximal with the property that for all u comma v belonging to C, right, there exists a path from u to v and from v to u. So a simple example would be so let us look at this directed graph, right, and as you can see, this is a strong component and this is a strong component, right, and this whole thing together is not a strong component, right, because for example between this vertex and this vertex there is a path only in this direction, but there is no path in the reverse direction. Further, no subset of this is a strong component, right, because of the maximality condition. Fine. Right. Let us also complete one small technicality which is often missed. This single vertex is also a strong component. Fine. So therefore there must be, inside a strong component there must be a path between any pair of vertices, right, and by definition we just assume that a vertex is connected to itself, and therefore a vertex which consists of a single set, a set that consists of a single vertex, right, and nothing else is a strong component. Fine. Okay. Given that we put all these definitions in place, observe that there is a very simple object that you can visualize, which is a decomposition of the vertices of a graph into strong components. Right. So because of all the definitions that we have put in place, right, we can partition the vertex set of the graph, of any directed graph, into strong components. Fine. In the worst case, what might happen is that if you do not have cycles at all, right, like as you see in this picture there are cycles here, right, every single vertex will form a strong component. Fine. Are the definitions clear? We have introduced the definition of strong components and a partition of the vertex set into strong components. Fine. Okay. Now we are in a position to visualize examples, right. So why is this important, right? So if one looks at the history of the problem, the first results on this problem, it occurred as an application of the then early search algorithms by Tarjan and subsequently by Kosaraju, right. So at that problem, at that point of time, if you look at the results, there was really no motivation except to design algorithms for some graph theoretic problems, right. So if you look at a textbook like Harari, right? On graph theory, these are important problems, right? So strong components and identifying strong components, right? So there are results about that, the fact that associated with the strong components in a graph, you can also write down another directed graph and so on, right? So the first applications were purely combinatorial and designing algorithms for these problems, right? But over a period of time, so here are the applications where you can design algorithms using the dynamic programming paradigm, right, or the recursive algorithm or recursive algorithms where you could solve problems on these strong components and put together these solutions, right. So this was definitely one place where decomposing a graph into strong components played an important role, and there are quite a few applications. The second one is an OR, right. So where you could consider this as a network and partition these networks appropriately and associate supply nodes and treat some of these nodes as demand nodes, right. So in operations research, to consider the most interesting one, the two most interesting ones according to me, right, are not these two, but the connection to Markov chains, which are very special kinds of probabilistic processes or stochastic processes, right? And some Markov chains have what are called stationary distributions. And one of the necessary conditions is that the underlying state space must be strongly connected, right. So that's definitely one condition. The fourth one is really with the advent of the internet, and one classic example is that you can think of the Facebook graph, right, and you can ask for communities, right. So where people know each other, right. So essentially it's discovery of communities in social network analysis. And the kind of questions people are interested in is that you have a network of people, you can imagine this to be the Facebook linkage graph or the links in the internet, and you want to ask, with respect to a particular topic, is there a classification of a society into communities having a certain property, right? And you can also ask questions like, who are the central people in a community? For example, if you have a particular individual, right, and if you remove this individual, the neighborhood, the people that this person is connected to, right, get broken into multiple components, right, multiple connected parts, then you can in a sense assign a measure of importance to this person in this network, right. For example, by removing this person, if you have fragmented this whole world, then you can say that this person or this small set of people are the ones that keep this society connected, and so on and so forth, right. So the key word here is applications in social network analysis. And yeah, so in a sense, as you can see, the first algorithms were for simple combinatorial interest, where you wanted to design algorithms for very popular graph theoretic questions, and this is starting from 70s right up to now, right. So the problem is remained very interesting. So at the end of this lecture, I'll also pose some questions which are very interesting, right, relating to strong components. Okay, so let's move ahead and look at algorithms for strong components, and before that, let's visit the primary tool that we are going to work with, which is the DFS. It's a recursive algorithm, as many of us know, right. It's called depth first search, right. And it essentially gives you at the end of a depth first search traversal of a directed graph, the information that you get is a data structure called pi that encodes a spanning forest. So basically for every u, right, in a sense pi of u is the parent of u, and I will explain what parent is, but I am sure you must have, some of you might have seen this already. Right. Then it also gives you a data structure, an array which is u, right, the first visit time of the vertex u, and another array which is f of u, which one can think of as finishing time. At u. Then the edges are classified and let me call these this classification white edges. In other words, these are tree edges. Then you have what I will call gray edges, which indicate cycles or back arcs, and black edges which indicate either forward or cross arcs. Right. So the edges are classified by depth first search. So the data structure that you get is you essentially get something that encodes a tree like structure. We will elaborate this shortly. You also get some information about when a vertex was first visited, a finishing time when a vertex is finished with, I will explain what this means, and a classification of edges into those that store some connectivity information, those that store some information about cycles in the graph, and one can think of other edges, right, and we will see what possibilities exist. Right. So this is basically what DFS gives access to you, right. So at the end of a depth first search on a graph. So let us look at how these data structures are populated, right, as a quick review, and if you have questions please feel free to ask me, right. So I am trying to get to the strong components part, but if there is anything that you are not sure of, please do stop and ask. Yeah. Yeah. Okay. So it's a stochastic process, right. So for example, yeah, I wonder if I should take this here or should we do this later. It's a probabilistic process where you can toss a coin and move to a next state, right. So it's a random, you can imagine, so let me draw one example of a stochastic process for you. So let's assume that this is one state, let me call this the 0 state. Now you have a 1 state, right, with probability half, you go from the 0 state to the 1 state, right, and with probability half, let us say the system comes back from the 1 state to the 0 state, and with the remaining probability here, let us say the system goes to a D state for some dummy state and stays there forever. Think of this process, right. Okay. Now one of the questions that people are interested in is that does this have a steady state distribution? Don't think of a probabilistic, don't think of probabilities at all. Let us assume that you start off with 1 unit of mass on this node, right, and now the system actually does the following. It distributes this one as half here, right, and half here, right, and then takes this half and sends 1/4 of it here, right, or half of whatever is here, and the remaining to this particular node. And now you can ask this question, does this mass get uniformly distributed? Does it have a steady state after which the distribution of this one unit does not change at all? Right? It's a valid question to ask, and it's known that such distributions are possible for special kinds of processes of this kind, and the strong connectivity of the underlying network is very important. Right? For example, you can see that this network is not strong connected. For example, from here you cannot get to any other node. Fine. Yeah, I'm sorry I'm not answering it, but if I did answer your question, then I wouldn't be able to do other things. Yeah, maybe I can explain. All right, so let's see how this data structure is, these data structures are populated. So the first step is an iteration on the vertices. You can choose any order in which you want to start exploring your network or the graph. It's an iteration on V belonging to V. Okay, so there's one more thing that's necessary for the algorithm to run, which is the color of a vertex. It's initialized to white. And it's actually straightforward, right? I'm just doing this so that one can analyze some properties of this algorithm. One could view this as a walk or an exploration of a tunnel system by a mouse, right? So you just start off at a particular, you initially, all the places are unvisited by this mouse, right? And then you can say iterate on V, right? Set up a counter, right, which is, let me put this as 1.1. Initialize time to 0, right? And iterate on V, right? First check is to check if color white would mean that V is unvisited, right? And now you start an exploration at V because V is unvisited, right? And the steps would be, and this can be seen recursively, so this part is a recursive. This part is recursive from now on. So where you iterate on edges leaving V. So let me just draw this picture. You have V, right? So these are the different edges that go out. Let me call these U1, U2, and U3. Right? So you set up an iteration here, right? And now you initiate a, and let's call this depth first search exploration. At UI, right? So for every endpoint, you start a depth first search exploration, and of course, at the beginning, the kind of stuff that you need to do here, right, is that you check if UI is visited, right? So you have this color information, right? And if a color is white, you check if color is white, in which case you change the discovery time is the current value of time plus 1, saying that you've come here at this point of time. And when you return from this recursive call, right, so on return from this recursive call, update f of ui is equal to time plus 1. Now also here, when you change color, you change color to gray, right? And on return, before you increase this, you change color to black. I'm doing this very fast, so but I'm sure you'll be able to visualize this. So let's just see this. You start at a particular point at a vertex u, right? You first check if you visited this place before, and how can you do that? You can check the color, right? If it's white, this is the first time you visited it, so you put a marker here, right? So how do you put this marker? You convert the color to gray, right? And then you keep track of the time at which you discovered this vertex, right? Okay. One more thing that I forgot. If it was white here, you keep track of the vertex from where you came to this vertex, and pi, the parent of u, is set to v, right? So let me make this change here. pi of ui is equal to v. Right? I hope I am not losing any of you, but please stop me. Right? So you come to this vertex, you see it as white, which means that this is being visited for the first time. You update the discovery time for this as the current value of time plus 1. Right? Then you keep track of where you came from and observe that this is a unique value. Right? So the basic thing is the parent is ensured to be a unique parent, you keep track of that information, and then you go ahead and explore the rest of the world from here. Right? How does this happen? It happens recursively. You look at all the edges that go out of this place. Right? And when you have finished returning from all these recursive calls, which means you have explored all these edges, right? So then you will exit from this place. When you exit, you update the color to say that you visited everything that can be reached from here, and you encode that using the color as black, and f of ui, the finishing time, is said to be the current time plus 1, at which point of time, in a sense, this vertex is finished. Right? It is done. Everything that is reachable from here is done. Fine. All right. So let us just write some promises of this that this algorithm makes. Right? The first one is that everything that is reachable from a starting vertex, right, will indeed be colored black. Right? So let us write this down. If V is reachable from U, and if you start a depth first search at U, then color of V is black. The color of V is black, right, at the end of this execution. Okay. And therefore, because we are doing an iteration starting at every V, right, at the end every vertex will basically be black. Right. So consequently, for all V. This is obvious. The second factor is not so important, right? It is not useful at all. The third one is more interesting. As you can see, pi encodes a rooted forest. A forest is a collection of trees, right? And pi encodes a rooted forest. So let us look at this example. So let me call these vertices as 1, 2, 3, 4, 5, 6 and 7. Let us say your DFS, the first iteration starts at 4. Right? So what are the vertices that will get visited in this DFS? So clearly the first step will bring it here, right? And then you will visit this. So you will give this visited at the time instant 1, right? Let me put a circle around the time instance. Then you will visit this at time instant 2, then this at time instant 3. Right? You will also explore this and find that this was actually grey. Right? Then you would have discovered that every edge that can be explored from here is done. You will return, this will become black, right? And that will happen at time instant 4. Same thing will happen here at time instant 5, right? And at time instant 6 you would have come back here. Fine. Observe that everything that is reachable from here is taken care of and has been given a starting time, a discovery time and a finishing time. Okay. There is also one another piece of information where this edge would have been classified as a grey colored edge because this encodes a cycle. So when do you say something encodes a cycle? If you are at a particular vertex and you encounter an edge, and that edge takes you to a grey color vertex, observe that if something is grey and you are at a particular vertex, it is very easy to observe that this is a descendant of this vertex. In other words, so when you start at 1 and 2 and 3, observe that this is still gray, right? And this edge is being taken, so this encodes an edge where one endpoint, right, the head of this edge is gray colored, indicates the presence of a cycle, right? And therefore, the gray edges classify these as cycles, and the white edges are these edges. The first visit to a vertex, right? So these are white edges, and what you see is a tree-like structure, right? And why is it a tree-like structure? And it's a very important thing, that the parent by design of the algorithm is a unique parent for a vertex, right? And therefore pi encodes a rooted forest. And why is it a forest? As you can see, the tree that you get from the pi data structure is this path. Then you will, let us say you make the mistake of exploring something here, so this will be one forest because nothing else to do, and you would have colored this black. Then you will start this search here, and maybe you get this path, right? And as you can see, you have a forest of 3 components. This is a white edge, sorry, this is a white path consisting completely of white edges, this is another white path consisting of white edges, and so is this one, right? Let us also color, so let me write, this is a white edge, this is a white edge, this is a gray edge, right? Then this is a white edge and this is a white edge. And observe that this edge will also be explored from here, it goes to a black one, we call this a black edge, right? So it's across 2 forests, right? And therefore this is called a cross edge, we won't use it as of now. And this is another gray edge. Right? So this is essentially all that I need, right, to go ahead and discuss the algorithms for discovering such strong components. So let me just summarize. It's essentially a recursive algorithm that you can think of by placing markers whenever you visit a vertex first, and you track the edge that brought you to that vertex. Then you classify edges as that cause cycles, right? And then you keep track of edges which bring you to new vertices, so to speak, and then you track edges which bring you to places that you have visited earlier, right? Those are the black edges, right? So at the end of the depth first search, this is the information that you have. One another very important thing to notice is that depth first search itself visits or explores every edge exactly twice, right? For example, you look at this edge, right? The data structure which contains this graph is touched when this edge is traversed forwards for the first time when it is a white edge, and when the recursive calls return, you can visualize this as traversing backwards, right? Therefore, every edge is visited exactly twice, and this counts the running time of the algorithm. This is a representative for how long this algorithm runs. This is a 2 times cardinality of E is the time counted by the recursion part, and there is this outer iteration which explores different parts, right? That gives you plus a cardinality of V. Fine. All right, so this is essentially the running time of depth first search, and this is the data structure that we have. Let us just observe one queer thing, right, where the order in which you consider the vertices can give you different outputs, right? And that's exactly why I chose to start the depth first search by looking at this vertex after this and not here, right? Observe that the forest has 3 components here in this run, where the first vertex was here, you explored this part of the world, then this one and this one. On the other hand, if the iteration had started off an exploration from here, then here, then this whole thing would have been a single component, fine, would have occurred in a single tree. That's basically the point, fine. All right. Okay, so this is the black box. So I can pretty much erase everything except for this part. So this is the data structure that we have, right? And are there questions at this point of time? Yeah. Exactly, right? So that's without going to the board, right? So it's very clear to you that this is an exploration where you come to a vertex, you inspect whether it has been visited before, right? if the color is not white, then it means that this vertex is visited before. That is clear, right? If it is equal to white, right, that means that this is the first time this vertex is being visited, right? Now, what you must understand is that in the iteration there is a single edge, right, which has brought you to this particular vertex. That is this step in the iteration. Iterate on the edges leaving a vertex V, and at V, this recursive call essentially checks if the color is white. If the color is white, then you keep track of V. What is V? V is this vertex, right, which brought you to Ui, and you keep track of the information that pi standing for P, the parent of Ui, is V. In other words, the vertex where I was before I visited this vertex the first time is called the parent. Fine. So, it is well defined, that is what I want to emphasize, except at the root node. At every other node, wherever you start, right, except at that node, at every other node, pi is well defined. Does that answer your question? The color of edge 3, 5, good question. That's also black.
Suppose if another first get iterated first,
yeah,
then the color might change.
Exactly, good point, right? So, if I started off from here, observe that this whole thing will be in a single forest, and this would have been a white edge. That is a good point. Yeah. Right. There was one more question.
You said edges, vertices you go through twice.
Every edge. No, you can count it twice. If you want to estimate the running time of this algorithm, observe that it is a recursive algorithm, and you want to come up with a measure of what is the complexity of this algorithm. How much time does the algorithm take? You can count the edge twice. That is, when a recursion is made, when a recursive call is made, an edge is considered, right? And when the return from the recursive call happens, again it is like coming back on that edge. So, every edge gets counted twice. Exactly, isolated vertices, right? Yeah, you are right. So, basically every vertex you iterate once, you have to check its color, that is this loop, right. So, if you assume that this is a constant time comparison, then definitely there are number of vertex, number of comparisons. Further, you look at every edge, you will agree that every edge is indeed visited in this whole procedure, right, and it will, you can count 2 units of time for every edge. 1 unit of time is when the recursive call is made, and 1 unit of time is when the return is executed. That is 2 times the total number of edges. Fine. So, possibly your confusion is, how does this a measure of time, right? So, my answer to that question is that you are using, right, the number of edges to measure, to stand as a representative for time, like you count number of comparisons in sorting algorithms, similarly here.
As it gives different outputs in different runs, so communities might not be different.
Let us not come to that, right. So, but let us fix one thing. If you fix this order over which you will iterate, then the answer is unique, nothing changes, right. All that I pointed out is that if you had different orders of edges, then you will get different decompositions of the network. We are still not there at communities, right. So, it is just connected structures. Fine. So, now we are going to use this to come up with strong components. Okay, fine. Okay. Any ideas for coming up with strong components? Can somebody come up with a algorithm, need not be efficient, but completes in polynomial number of steps?
Any indication of a gray edge? Anywhere there is a gray edge, you have to look around that.
Okay. Yeah, that is trying to be more sophisticated, and we will use something like that, but something straightforward which will guarantee that here are the strong components. Yeah.
Yeah. So you go in the reverse order. Okay, first you do a DFS, setting one particular thing that will give you a particular set of strong components, and then you sort of set up a reverse.
Okay, that is still also sophisticated. Yeah, you are right. So, we will do something similar.
Even more sophisticated.
Yeah, that is even more sophisticated. Let us do something very simple, right. You want to know one strong component, you simply instantiate at a particular vertex take a particular vertex and look at every pair and check if there is a path, right, between the two vertices. For every pair u comma v, fix a u. For every other v, check if there is a path from u to v and v to w, and put them all into one bag. Right. Observe that this two-way connectivity is an equivalence relation. If there is a path from u to v and a path from v to u, and if there is a path from u to w and w to u, there is also a similar structure between w and v. Right. So just transitivity is something that you need to worry about. So yeah, right. So here is a trivial algorithm. So let me erase this part. So all that I am saying is this. In a strong component, right, which relates u and v together, u and v are in a strong component. So if you think of this as a relationship between u and v, is an equivalence relation. Correct? So it's a relation that partitions, it's a relation defined on the vertex set, right? And clearly we know that the partition of the underlying space by equivalence relation is a unique partition. Therefore, the first observation that we make is that the decomposition of the vertices into strong components is unique. Fine. That's simply because you can see that this is an equivalence relation, right? So u is related to u. If u is related to v, v is related to u, and u is related to v and v is related to w, which is this picture basically. This is u to v, and this is v to w, right? And then you have maybe v to w. No. So this is v to u, and v to w is a path like this, and w to u is a path like this. As you can see, there is a path definitely from u to w and a path from w to v. Right? Of course, through v there is one, there might be a better path or whatever. Right? Therefore, this is an equivalence relation. Right? Therefore, the key thing that I have proved to you is that decomposition into strong components is unique, right? So there are not two of them. Right? And definitely, by definition, it indeed exists. This is another very important thing. Strong component decomposition does exist, and if it does, and it's also a unique decomposition. Fine. Okay, the trivial thing is to discover one equivalence class, right? And you can write a very bad algorithm, but which definitely does work, is to create one equivalence class by checking pairs of vertices which are related by this relationship. Essentially enumerate every pair u comma v, check if they are related by this relationship. That can be done by the depth first search algorithm itself, right? And that will tell you one equivalence class in your equivalence relation. Is this clear? Right? So here is the algorithm 0, right? Iterate over all pairs u v, right? And put all those vertices which are in one strongly connected component, and this can be done by two queries of depth first search. It's a bad algorithm, right? So we are missing a lot of things that we can exploit, just ignoring every other thing that depth first search gives us, and we are just using whether u and v have a path in both directions, right? And therefore you can create one equivalence class like this, and clearly this is a polynomial time algorithm. That's it. I mean, we don't have to say any more about it. All right, so let's do something a little more interesting, right? And not significantly more, right? So let's call T1, T2, and T3. Let's consider, okay, maybe just T1 and T2. Right? So you run depth first search, the first ones, and what you get is a partition of the vertex set into two trees. Right? So which means that there is a special vertex, let me call this R1, and all these vertices reachable from R1. Right? And then you have R2 and everything that is reachable from R2. This is well defined. Right? Okay. Secondly, you will also observe that the finishing times of R1 and R2 obviously have to be distinct numbers. Right? So without loss of generality, let us assume that the finishing time of R1, right, because I have drawn it to the left, is smaller than the finishing time of R2. Right? If you have lost what the finishing time is, this is the data structure. Okay, I should not have used this parenthesis. Right? So what did you do? This is the output of one run of depth first search. All these, this triangle that I have drawn is representative of all the white color, the tree edges, and same here. Right? And this finishing time is later than this finishing time. That is, f of R2 is smaller. F of R2 is larger than f of R1. Okay. Now here is the modified algorithm. DFS again, and in the outer iteration, let us do exactly what one of our friends here suggested. Right? Order vertices in decreasing order of finishing time. Decreasing order of f, and in which graph? Right? In G reverse. Right? So what do I mean by G reverse? You consider, so this was done on the graph G. G reverse is the graph where every edge is flipped, right, or turned, the arrow is oriented in the opposite direction. In other words, if you have an edge like this, right, you just turn this edge to be in this direction and do this for every edge. Fine. Is that clear? And now you start your DFS from R2 and explore anything that you want. Right? Run your DFS exploration. Let us assume that you get T1 prime, and let us say you get some T3 prime. Right? So I hope all the steps are well defined. Now we need to analyze properties of this. Right? This is these are the trees that you get from one run of depth first search, some arbitrary order of the vertices. You also get this finishing time business. Right? You run the second depth first search on the reversed graph. All the edges are oriented in the opposite direction. Right? And you just change the order in which the vertices are processed. Right? You select a special order which is in decreasing order of the finishing times that you had obtained earlier, and do DFS again. Right? And now what do you have? Let us say you have a decomposition of the vertices into trees. Now I claim that this is a strong component decomposition. Each tree is a strong component. Fine. Is the algorithm clear? Yeah, just take the graph and just reorient the edges to be in the opposite direction. That's it. Fine. That's a good question. We'll come to that in a minute, right? So that kind of issues, we'll come to that in a minute, right? So let's assume that we can do that with the graph. Fine. but yeah, we'll come to that in a minute. Right? So maybe if you think about it, you can implement the algorithm by keeping that in memory. Right? So what you could do is that you are at a particular vertex. Normally you would have gone out on those edges which are going outwards, so to speak. Right? Instead, what you do is you go out on the edges which are coming inwards. So you really don't have to reconstruct the graph. Right? You can tailor the program. You can tweak an existing program to choose the other edges. Right? So travel on the incoming edges. Right? So the implementation does not change drastically. Right? All right. So is the algorithm clear? Okay. So now let's observe one property. Let's look at just T1 prime alone and check that it's a strong component. Right? Fine. So let's look at T1 prime. What is the vertex, the root vertex in T1 prime? Let's just see. Right? So it is this vertex which had finished last. Right? So let us say this is V1. Let us say this is V. Right? And in T1 prime, it was depth first search which started at V in the reverse graph. Right? Okay. Now let's just see. Okay. So you had this vertex V, and let's look at. Okay, let's look at any one neighbor here. Right. So you have this edge VU in this graph, and yeah, so let's now I need to argue that there is a path, right, from we need to argue that there is a path from U to V in G. Right, so this is what we need to argue. What are all the properties that we know? We know that the finishing time of U is definitely lesser than the finishing time of V. That's something that's very clear, right? Because that is our premise. Right? The starting vertex is the one that had the largest value for the finishing time. Right? So therefore, we know that that particular vertex U, which is adjacent to that particular vertex U, which is adjacent to V in this particular decomposition, in the original graph finished before U. Right? Okay. So let us just look at the possibilities of Yeah, so let me repeat this again, right? So in T1 prime, right? So V is the root vertex, and let us consider one neighbor, right? In T1 prime, which is the depth first traversal of G reverse, right? And now let's look at this particular neighbor and let us understand what the structure is, right? So this edge is in G reverse, right? This is in G reverse. What we do know is that f of u is smaller than f of v. This is clear, right? Okay. If f of u is smaller than f of v, what are all the possibilities? Inside this component, right? Sorry, inside this particular tree, it's clear that this vertex would have had the largest finishing time value, right? Okay. Now, it's indeed quite possible that this vertex u could have been here, right? In which case you are done. Okay. Why? Because from u there is a path of white color edges. Remember that it's a tree, right? And therefore you have found a path from v to u, right? What's the other possibility? The other possibility is that there is u is here. Right? Now, because u is here and this edge is in the direction v to u, right, then you should have seen the edge in this direction, correct? In G. Clear, right? Let me repeat this again. This is an edge in G reverse. Therefore, it must show up as u oriented towards v in G itself, right? And therefore it shows up like this here, right? So one possibility is that u is here, in which case observe that there is a path from V to U, definitely, right? Okay. So, and does that take care of it? Yeah, good. Right. Okay, so let me just complete this analysis. So there is a path from V to U, and also remember that this is a edge in the reverse direction, right? Therefore, U and V are in the same strong component. That is clear, right? So if you find an edge of this kind, the case is that U is in the same component or in the same tree that contains V, right? Then clearly U, V are in a cycle. There is a path from U to V and an edge itself from U to V and a path from V to U here. So we need to do the same analysis here, right? So let me remove this to avoid any confusion. This is the second case, right? Now let's exploit the fact that U had finished before V. Could that have happened? Let's see. Let's assume that had happened, right? So remember that we have that f of U is smaller than f of V. So let us draw a picture. There must have been a time at which U was visited, right? Okay. Now, then U had finished, right? But observe that you have also seen an edge U to V, right? Now, therefore, if this pattern occurs, right, then it means that the finishing time of V, right, should have been earlier than the finishing time of U, right? So therefore, this picture cannot occur, right? Therefore, if you find an edge of this kind, right, then U and V should have been in the same tree in the DFS here, right? So therefore, every edge that you see here in this particular tree indeed does correspond to a or witness to a fact that there is a path between two of them in both directions. Is that clear? So because we have checked both the properties, so we just analyze this for one edge, right? Either both of them occur in the same component or both of them occur in different components, right? And now we use the fact that the finishing time of one is smaller than the finishing time of the other, right? And we have got a cycle here, right? So this we have done for the root vertex here in the first component and one neighbor of this guy. We have not done this for everything yet, right? But how does one push this further? Let us look at, right, U and W, right, and UW is this edge. So let us recall the rule that we have applied when we do the depth first search. Whenever you look at the edges, you do this in the decreasing order of the finishing times. Let us not forget that, right. The DFS, whenever you apply any recursive call at a vertex, you visit the edges in the decreasing order of finishing time, not just at the top level, because it is a recursive specification, and every recursion, that is the order in which you will inspect the edges. Therefore, the same analysis works for U and W also, right. So that is because of the recursive specification of what happens, the order in which you inspect the vertices. So what is very clear to us that if you look inside a particular tree here, there is a path from any two vertices, there is a path in both directions between any pair of vertices inside the tree, fine, okay. Why is it maximal, right? So that is one property, right. So therefore we need to argue that there is a maximal set in G. What we have argued is that for every pair there is indeed a path. So let us finish the proof that it is indeed maximal. Proof would be by contradiction, you assume that it is not maximal, fine, okay. So let us look at this particular vertex and let us assume, let me draw this picture again. So this is U, this is a component, you know that in the graph between any pair there is a path in both directions, that is clear, right. By the way, I will just complete it. So this edge is here, this edge actually stands for a path in both directions. Similarly, the next edge also stands for a path in both directions in the graph. Therefore, clearly between these two there is a path in both directions, Alright, so let us assume that it is indeed not a maximal set. So which means that you have a y, right, that is not inside this component, right, but it does have a path, right, in both directions to some vertex here, right. In other words, if you put all of these together, you have the desired property of connectedness in both directions, but y is in a different component. Can that happen? Right. So let us just see this, right. So let us consider a path from here to here, right, in the graph, right. So we know that by our assumption, we are doing a proof by contradiction, that T1 is not maximal, which means that there is a y that you can add to T1 and you can get a larger set with the desired property of connectivity in both directions. Let us assume y is such a representative, right. Let us take this path from y to the first vertex in this set, right, and maybe there is another path from here to y. That is in the graph, right. But just focus only on y to this vertex and let us make the analysis simpler. Let us assume that y has one edge. How would this edge show up as in the reverse in GR? Right? It would show up in this direction, and therefore the depth first search here should have actually added y to this component, at least for the first component. This is a clear analysis, right. So for the first component, it can't happen that y could have been outside it with this particular pattern, right. Fine. So therefore one thing is clear now, the first component is a strong component in the original graph, correct. So we already argued that inside this between any pair there is a path in both directions. We have also argued that there cannot be a vertex which is outside this, right. So essentially the T1 prime, right, is a maximal set, right, it is a strong component. Right. How would you complete this? You just remove it and the same analysis will work, right, because again you may worry that something which was not a strong component, something which was a strong component, right, could not have had its connectivity via T1 prime, which is indeed true, right. So the first one, right, the first vertex, right, the first component is indeed a strong component. Remove this and repeat the same analysis, right, and you will conclude. It's this finishing time that tells you that such an edge cannot exist, right. So if there is an edge uv here, it would show up in the component, right, that contains, yeah, so it should have been vu, right, it would occur in the same component here and not elsewhere, right. So therefore the running time is essentially that of 2 DFSs, and an additional data structure to reorder the neighborhood based on the finishing times. All right, so is this clear? Right, so let's just look at the crucial steps again, right. So one DFS, you get the finishing times, and the second DFS where recursively you select the order of the neighborhood based on the finishing times, right, and run your DFS, and what you get is this partition. We observe that each one has a nice property that it's a strong component. Right. In particular, we analyzed it completely for the first one. Are there other questions? Otherwise, we can move to some interesting related issues. All right, so it's a linear time algorithm, obviously, with 2 DFS calls. So let me just pose the first interesting question which you can explore. With just one depth first search, can you decompose the vertex set into strong components? Fine. A very closely related problem can be done. In an undirected graph, if you wanted to partition the vertices into such a structure, right, so it turns out that they are called biconnected components. Right. See, for example, if I remove the arrows, right, if I discarded the arrows in the sense that make all the edges bidirectional, this is called a biconnected component. This is another biconnected component, and this is another biconnected component. And in one pass of depth first search, right, very carefully you can discover that this is one set, it's another set, and this is another set. Right. So why is this question interesting? Biconnected components is just one DFS and an additional data structure, right, which is called low, and I will just quickly one DFS plus another array. All right. We will come to this in a minute. Let me pose the other question. So question 2 is that you know that the strong components are, so this is component 1, this is component 2, and component R, right. So the question that I ask is, can we identify a small set of representatives, right? Let me call this R1, R2, RR, right, such that if somebody tells you R1, it uniquely defines C1. Right. So in essence, you have this equivalence class, right, and R1 is a subset of vertices such that every other vertex here, right, the two-way path between the two of them is witnessed via R1. In essence, you do not have to store any information about the vertices outside R1. R1 is a representative set. Right. So let us just see an example of this thing. Right. Let us just go back to this example. Right. Now you have this vertex, then you have this vertex, and let me add this. Right. Yep. So as you can see, this is strongly connected, right. So this one in some sense has all the necessary information for you to infer that this and this also belong to the same strongly connected component. Right. Therefore, if you are trying to come up with a data structure, and that somehow is closely related to his question about if the graph is very large, how do you make a copy of it, and how do you change the edges and so on, which we handled very easily. But here is one concrete way of trying to save on space. Right. So given a strongly connected graph, can you come up with a small set of vertices, right, which essentially is some sense the representative of every equivalence class. Right. And as you can see, it is a well defined question. In the worst case, you can always report that the whole equivalence class is very important. Right. So this is one question. I do not know the status of this question. So this is something that I invented over the last 2 days as to what would be an interesting optimization problem associated with strongly connected components. Right. So given a digraph, this is unique, right, and inside every equivalence class, can you pick a small set, right, come up with this small set which is representative. Right. So of course there are some thoughts that I have on it, connecting them to vertex separators and so on, but let you explore. Yeah, so I guess I've used up my hour. So if there are questions, I can answer them. Yeah.
You spoke about C1 and R1. Why can't we take R1 as a single vertex itself, like a set lead or something? Lead of set. Because vertex is connected to itself. Strongly component. It's a
Correct.
strong component.
Correct.
So in place of having three vertices as a strong component, can't we have it as a single vertex itself?
Okay, so my question is, if I just give you the single vertex, is it a representative for connectivity between every pair of other vertices which you have left out? So the way of thinking of my question and your counter question is that, is there a single vertex here which represents the fact that there are paths in both directions between, say, u and b, and let us say this is x, right? So if you keep just one element from here, it could be because maybe everything else has paths of this kind in both directions, maybe this edge is here. In this case, clearly this vertex is sufficient for you to discover that u and v belong to the same strong component. But I don't think in general this is the case. For example, if you go back to this example, just keeping any one of these three vertices does not solve the problem. It is insufficient for you to infer that these two have a path between each other in the graph.
All the vertices have path between each other.
Yeah, but just keeping this vertex as a representative does not help you infer that information.
That's why.
Pardon?
Why can't we infer that?
So you will have to see, for example, if I store all these information, then to know if there is a path from, say, let us call this x to y, right? So if I know that for both x and y, there are neighbors in both directions inside this set, then I know that x and y are in the same component. Observe that that's a single query to your data structure, right? So if I keep this information, this is concocted in such a way that just by asking for the neighborhood of x, the in neighbors and the out neighbors, I can conclude that x and y are in the same equivalence class. Right? So here is an example where keeping one vertex is insufficient. So the goal is to be able to infer the equivalence class by quick queries. Right? Of course, your thought could be that, well, I can actually search and answer the question. So my question is that maintain as small a set possible, that whenever a question about x and y is asked, I have a quote unquote constant time answer from the data structure.
Can we say that R must be such that all other vertices in C, not in R, must have an edge that's an in degree and out degree to the set R?
Correct. Yeah.
A single edge, not a path.
Edge, single edge. Yeah. So for every pair x, y which is in the same equivalence class, I should be able to find an edge coming in to x and an edge going out. Yeah, so that's correct.
You also want R to be strong. No,
Yes, I want R to be correct. R should also be strongly connected. Yeah, exactly. I'm done. Thanks for your